Hello and welcome to the session. I am Dr. Akshay Kumar from School of Computer and Information Sciences, IGNOU, and I'll be discussing with you today about Dijkstra's shortest path algorithm. This is a very interesting algorithm. Now, shortest path. Most of us, when traveling, want to know which is the shortest path. As far as not the distance is concerned. Many a times we are just looking for time which will be taken to go from one particular place to another, right? Now, how can we determine the shortest path? However, this particular situation, remember, when we are looking into Google or so, that is a slightly dynamic situation, okay? Shortest path algorithm can work on a dynamic situation but not dynamically changing weights, right? So what it requires, once you run algorithm on static weights and suppose the value changes, then you can run this particular algorithm again to find the shortest path. So what is there? It's a very interesting algorithm and you should know it by heart, and this is something which will give you a lot of good insights how you can design algorithms. Okay, but one of the things which you should remember is that this algorithm also uses greedy approach. So greedy approach somehow is a very popular approach in designing algorithms in different situations. So let's go through the algorithm and thereafter its complexity, and then you will be able to work out how this particular algorithm you can apply in different situations. Okay, so what is the shortest path if I trying to define in a graph? What is the shortest path in a graph? So given a weighted, so when you are trying to define shortest path, you are trying to define it in a weighted graph. And in weighted graph, the weight may represent the time or the distance, right? Depending on what you exactly want. You want shortest time or shortest distance to travel. Okay. So given a weighted graph G with the set of vertices and set of edges, okay, if there is an edge between two vertices U and V, we say that U and V are adjacent. So this is the first definition. This is not the shortest path. This is the first definition. So if I am referring to A, any node which is there is a direct edge, then we say C as well as B are adjacent to node A. All right. So this is the definition. Though there is a path from A to G, all right, there are multiple paths from A to G. All right. So let's take a simple two nodes, A to D. How many different paths are there from A to D? I can go from A to C and C to D. That may be first path. I may go from A to B, B to D. That is my second path. Then I can go from A to B, E and D. I can go A, C, F, D. So there are multiple paths. All right. However, so paths may be many. However, adjacent is defined as a node which is C is adjacent to A because it has a direct path from A to C, and so is for B. So how do we define the shortest path? When the distance between U and V, okay, which distance is being defined by the weight, right? And I told you that this may not be the physical distance, it may be time depending on what you want to optimize. All right. So what you are basically finding distance between U and V, that is A and D. For example, if I want to find the shortest path between A and D, then one path is A to C and C to D have a weight of 8. Whereas if I travel from A to B and B to D, then the weight is going to be 2 plus 4, right? So total, this particular weight is just 6. So probably A to D, A, B, D is shorter than A, C, D. So which among the various paths is the shortest? That is what is determined by the Dijkstra's algorithm. All right. So we try to find the minimum distance distance. Okay. We find this minimum distance. In this particular case, this is the sum of these two, right? For all paths P from U to V, right? So the path, we choose the path which has a minimum weight. All right. Okay, so that is what is the minimum distance we call it, or minimum weight you call it. That is how we classify it. The otherwise there is no path from U to V. Suppose there is an edge somewhere H. There is another node here. So there is no path from A to H. All right. So that particular distance, we can say this particular distance is infinite. All right, and remember, infinite is, in computers, it's a very large number, that's all. But you will assign a number, all right. So that is how we define the, that is shortest path, all right. Now, what is the Dijkstra's algorithm? Let's try to first understand the algorithm, and then we will try to understand it with the help of an example. So first of all, the Dijkstra's algorithm is basically a single source shortest path. Single source shortest path is that it will take one node as the start node. All right, or this is the node from which all other nodes' distance will be computed, and that is one of the situation, or one of the case may be like so from node A, all other nodes distance. So single source. So source is one particular point. All right. All edges have non-negative weights. Now this is a requirement as far as Dijkstra's algorithms are concerned. Okay. So all the edges should have non-negative basically weights. There are certain cases where weights can be negative also, that we may discuss in the next session where we have such algorithms. But Dijkstra's algorithm works only for non-negative weights. It's a greedy algorithm, all right. So greedy algorithms, basically what we are going to select, we will pick and choose those edges, okay, or those paths which have minimal weight or minimal length of that particular path. Then two lists are created in Dijkstra's algorithm. Okay, first is the shortest distance from the source. So for every node, okay, so suppose we are saying A, then from A to A, what is the shortest distance? Obviously 0, but there is going to be some distance to B, some distance to C, some distance to E, right, D, F. So this basically a list of nodes for which the shortest distance from the source is basically chosen in one of the list, or it is going to be used. And another thing which is going to be used is predecessor node. After all, what I said was the path, right? Whenever we are dealing with path, the path basically is a set of nodes. So rather than keeping all the nodes into consideration, let's keep who is the parent or the predecessor of this particular path, all right, from this node. So for a node D, predecessors may be B, all right. So suppose there is a path A to D. So the predecessor of D is B and predecessor of B is going to be A. So that is how if I define the path from A to D. All right. So that is what predecessor node means. Then we will be maintaining a priority queue, right? And this priority queue is basically the list of nodes for which the shortest path is not yet final. Okay, so we have the weights of the node, which basically is intermediate weight, right? So they have not been found out, or you have not found out the shortest weight. However, you are trying to find the smallest. So far, whatever you have found, it has the smallest value. So among those, you will be creating a list or priority queue of node for which shortest path is not yet final. They are under intermediate consideration. Okay, and then we will be keeping this particular list will be sorted on the present value of the distance of the node. So whatever is the distance of the node in terms of weight, whatever weight you have selected. Okay, and then we have a set S of nodes for which the shortest path is determined. Okay, so finally set S of nodes for which shortest path is determined. So there is a node for them, it has been completed. So when everything moves from Q to S, right, that is the time our algorithm gets completed. All right. So this is where the Dijkstra's shortest path algorithm or example of this particular algorithm has been. Let's take or discuss that particular thing. So G. So first of all, Dijkstra's function takes 3 parameters. One is the graph itself. So what is a graph? Set of nodes and set of edges. So that will be known by this. W basically defines the set of weights, all right, between various edges. Okay. Then comes the set of, or it's not the set, it is the start vertex. All right. So the start vertex from which we are starting the entire algorithm. Okay. As it takes one start vertex, as we said, one source. So this is the source vertex. Okay. First step is initialization. So what do you do in initialization? For each vertex V, which is a member of the set of vertices, okay. So for every vertex, we will initially define the distance of each vertex to be infinite. All right. So every distance is infinite. We are starting with that particular assumption. Then, and the previous vertex to every such node is null because it has not been defined which is the previous or the predecessor vertex. So predecessor node is just null, all right, because no parent has been defined. Then, since this is the start node, so what we are going to say, distance of this start node is made 0. All right, because that's how it is. Okay, so this is my distance 0. So how this particular entire thing is going to look? Okay, so all these steps and the set of selected vertices which have been selected as far as shortest path is concerned, right now it is null. All right, and then Q is basically assigned the set of vertices V. So all the A, B, C, D, E and F and G, sorry, all the vertices then becomes part of the Q. All right, so this is my starting condition. Remember, this particular thing is 0. Okay, it has been put over here. Okay, so that is what you can see, the distance vector. All right, so distance vector is initialized to infinite. All right, however, distance of the start vertex, okay, which we have selected as A, has initialized to be 0. All right, then this is root, right? So this is basically the starting vertex, that's why we have labeled it as root, and for all other, the predecessor node is null. All right. So obviously root is just a pointer to the start node. Okay. That's why we have initialized it that way. and this basically A, B, C, D are the names. We will be keeping just that what these vertices, so what node we are talking about. So just to the naming convention, A, B, C, D, A, B, C, D, E, F, G. So all these nodes we are discussing in this particular algorithm. Okay, so this is initialization, looks very simple. What about the execution of the that is repeated loop? So how many times we repeat this particular loop? Till Q is not null. So Q is having right now 8 nodes. So all of them will be picked up one by one, and we will get our answer or shortest path from every node to every other node. And we will start from 0, actually, from the node itself. All right. So this is my priority queue. All right. Distance of V also contains this particular. So priority queue is basically consisting, that is Q consists of 0 and all other values are infinite. So which one will be picked up in the first iteration? Obviously in the first iteration, root will be picked up. All right. So extract min of the priority queue Q. So you have picked up this particular node. All right. We have picked up this particular node. Okay. So S is made S union U. All right. So what will happen? S will become basically in this particular case, S will now contain A because S was initially empty, null set. For each vertex V in adjacent U. Now adjacent U, as the definition of adjacent we know. So what are adjacent to A? C and B. All right. So these are the two nodes. So what we are checking? Two nodes are there. So let's start with B. Okay. Node B. T distance is just a temporary variable. So distance of U. What is the distance of U? This particular distance of node A is 0, right? So distance of U is 0, okay, plus weight of UV, okay. So weight of UV is this particular edge, A to B, okay. Weight of UV, in this particular case it is A to B, which is 2. That means for node B, this weight will be made 2 and null, which is its predecessor, A. That is with this particular iteration. Why? Because if T distance is less than distance V, it was infinite, it is less, right? T distance is just 2, okay. Decrease key in Q, okay. So decreases value in Q, that's what we want to do. And what happens? Distance of V becomes T distance and previous value of V becomes the value of the U. So U in this particular case is A. That is how this value will be converted over here. So now previous or the predecessor node to A is predecessor node to node B is A and the distance is 2. That's what has been updated. Same is the case with C. Iteration will go on, right? Because there are more than one adjacent nodes. So for C also the similar thing will be done. So the predecessor is going to be, the T distance is just 1, 0 plus 1. So this change is going to take place. So the value will be updated to 1. All right. So what we get? We get in this particular case, okay. Now what has happened? A has since been moved to S. So A is the set S. So right now set S has become A. These two nodes have now been added into Q. I mean, they are already into the Q, but then the values has been updated. All right. And these are the adjacent nodes which has been considered. All right. Their predecessor node is A. For B also predecessor node is A. For C also predecessor node is A. And the weight now has been updated to 1 for C and 2 for B. Now this is my priority queue. This is moved out, alright. This is in set S now. So my priority queue consists of all these nodes. Rest all are infinite, 1 and 2, only these two values. We got to select the smallest. We select 1. Alright. So as soon as we select 1, okay, so what we are going to do? So this now is going to be added into the, so earlier it contained A, now it will be added. So S will be now AC. So this we will be converting to green color as we have done for A, as we show the next slide. Alright. And the T distance. Now the distance, what are the adjacent to this node? F and this D. Alright. So what is the node for, what is the, first of all, what is the predecessor for D and F? Obviously C. For both these nodes, because that they are the adjacent nodes, right? So for both of them, the predecessor is C. And what is the weight? Weight is going to be, T distance is basically distance U. Distance U is 1. And weight of UV happens to be 7. So this weight is changed to 8, right? So this weight is going to be 8 now. Alright. And here it is going to be 1 plus 6, 7. So this weight will be converted to 7. Alright. Obviously this condition is true. That is why the whole operation is going to go on. So this algorithm will result into change in the value. So what are the change values now? The change value now you see, C is now permanent. Alright. This value is permanent. B is not yet permanent. AC have been selected. Okay. This forms my set S. So A and this forms my set. That is the permanent set. Now I am having changed value here 2. So my priority queue consists of these 3 and these 2 infinite values. Obviously 2 is the smallest. So I will be picking up node B from here, this particular priority queue. So when I pick up the priority queue from this particular priority queue B, what I get? This 2 becomes permanent, okay. This B becomes permanent, B will be added. So it will become ACB, this particular S. Set S is now ACB, alright. What addition? Now E. For E, the weight is going to be 2 plus 3, right. So for E, the weight is, earlier it was infinite, now it is 5. Predecessor is B. What about D? So for D, the weight is 2 plus 4. Alright. So 2 plus 4, this is going to be 6. 6 is less than 8. Alright. Since 6 is less than 8, therefore this change is going to take place over here for D. Now the predecessor will become B. And the weight will become 6. Alright. So that is how the updating is going to take place. Okay. So now what you see? This node is already been done. C, A and B. These 3 are already completed nodes. These are the part of S. Okay. Initially. Okay, 2, 1. So these 3 nodes have been done. Over here, now you can see the predecessor is B. It has changed from C to B. Okay, so D's predecessor now, this particular node, this particular link which was red earlier now is no longer red. Okay, because A to C to D is not a shortest path. all right, as the weight of this particular link was 7. So 1 plus 7, that was 8. Now we have found a shorter way so far, all right. So this is how it is worked. Okay. Now look into the next iteration. Here, shortest of them or the smallest of them, this is S, this is Q, all right. So this is my Q, and this from Q, E happens to be the node with the smallest distance, right. So I'll make it permanent, okay. So I'll basically not permanent in the sense I'll add it into S. So S, which was A, B, C, now E will be added, A, C, B, right. So A, C, B in that particular order, okay. So A, C and B, and E will be added into it, all right. E will be added, and there is another link from E, only one, there is an adjacent node. And what is the weightage of D because of this particular link? 5 plus 5, so this is 10. Obviously 6 is far less than 10, right. So this particular path is not the shortest, so this is not to be considered. It is not going to make any change because T distance is less than distance V. No, it is incorrect. So it is not going to be changed, this particular value, that is the value for 6. It will remain 6BED, all right. However, this will be added. Okay, what is going to be the next iteration? Okay, from now this has been added to S. So in the next iteration, 6, 7 and infinite. Obviously 6 is the least. So 6 will be added to this particular group. So this group is going to be, that is S is going to become A, C, B, E, and now D will be added to that. All right. Now D has been added at that point of time. So B is its predecessor. Now it has been that added to the set. Now no more changes will be there in the weight as well as any other predecessor node. Okay. So D is now becoming part of S. So this whole thing now has become S. All right. But as we add D, all right. So the weight of D is 6. All right. So 6 plus 9, 15. Okay. So no changes needed here. 6 plus 2, this becomes 8. All right. For G. That means G, there was no earlier nothing, null was the predecessor. Now we will say D is the predecessor for G, and the weight for D is not infinite, it is going to be just 8. All right. So this is going to be changed to 8. All right. So this iteration then we show here. So A, then C, B, E and D. Now they are all part of the set S, okay. And what we are left with? F, we have a predecessor C for F, okay. And this particular case, in this G case, what we have said that it is 8 and the predecessor for G happens to be D. All right. So this is how it's going to look like. Okay. Still the algorithm is not yet completed. So from 7 and 8, which one will be picked up first? Obviously the 7. So F will be added now. All right. Since F will be added, will F cause any change? The adjacent to F is G definitely, but 7 and 8 makes it 15. Condition is incorrect, so no more change. So it will remain at this particular position, except F will be added to the set. All right, and this is my final position, where now this particular, all these things have already been added to S. Okay, that's why they are in green color. G is yet to be added, and there is nothing else to be done except that D is to be added to this particular S node and make it green, and rest all the edges doesn't count now. They actually are not needed because they won't be required anymore. So what we are getting as a final graph, the final graph is going to be this graph. So we have A, then we have B, E, C, D, F and G. All right. So we are able to extract the entire graph here, tree from the graph, which basically are shortest, have the shortest distance. But what is the shortest distance from A to G? Which is the, how will you figure it out? Okay. Now, for that, let's figure it out with the help of this particular graph or this node, this information. So G, this is my G, my start vertex was A. So G, what is the predecessor of, in the graph I can easily make out, but this is what my output is going to be, right? So from this output, okay, so what is the predecessor? D, all right. So we go to D. So G's predecessor is D, all right. What is the D's predecessor? D's predecessor is B and B's predecessor is A. So this was my start vertex. So the path is going to be A to B, B to D and D to G. So A to B, B to D and D to G, and the overall weight of this particular path is just 8. So this is my shortest path from A to G. What about A to F? Okay. So what is the predecessor of F? C. All right. So we come to C. All right. And what is the predecessor of C? A. So this. So therefore this path is A to C and C to F. A to C, C to F, and the overall weight of this particular vertex is 7. A to C and C to F. You can clearly see it in the graph, but it is that is arrays which you got to determine. What about, now you can determine for all, but let us do it. Okay, so now for E, what is the path? Obviously A, B, E. But how do we know? A to E to B, E to B and B to A. All right. So this is how A, B, E is going to be the smallest path with a weight of 5. Now AD is going to be A, B, D, which is with a weight of 6, right? And this can be determined here also, like A, the predecessor is B, okay, and so A, B and D. All right, A, B, D. As far as AC is concerned, it is direct neighbor in this particular case, 1, and A to B, 2. Many a times even if you have an adjacent node, it need not be the smallest path sometimes. So you need to be careful. In this particular case, it turns out that both the neighbors are at the smallest distance, or both the adjacent nodes are at the smallest distance. Lucky in this particular graph. In other graphs, it may be slightly different. So this is the way we work out. First, what we do? First, we work out the metrics or the graph. Like we work out the entire graph and find the shortest distances, and thereafter we find the final paths from the shortest distance matrices. All right. So this is how the Dijkstra's algorithm works. It's a very interesting algorithm, and you should go through this particular algorithm very carefully and actually enjoy this particular algorithm. Now, what is the time complexity of Dijkstra algorithm? Well, initialization just take order V time, V vertices, right? While loop execute number of vertex times only, and in the inner loop inner for loop or inner while loop, what we get each edge in the adjacent U is examined only once, as the node is added to S once only. Okay? This for loop will run maximum number of edges times only. So updating distance E in Q will be number of edges times only. That is the time it will be required. So algorithm implementation will depend on the implementation of priority Q, that is Q. So if you implement through an array, then it will require order V square. Okay, or overall order is going to be V square. Or if you implement that priority queue with the help of binary heap, then it is basically V plus E, overall V plus E, and whole thing multiplied by log V. So that is the order when you are using the Dijkstra's algorithm. So let us try to summarize what we have discussed in this particular session, that the shortest path is the path with the minimum distance from one node, and Dijkstra algorithm works from one single source to all other nodes. Okay, so this distance can be in terms of time, or it can, suppose you are doing it for road, then it may be time or the actual kilometer distance. Okay. The Dijkstra algorithm finds the shortest path from single source to all other nodes. The weight of edges should be positive, and time complexity of the algorithm depends on the implementation of priority queue. With this, we end this particular session. Thanks for being with us.